I call it example of spectral analysis. And as a complete spectral analysis, something you will do very often in this chapter, many questions in the yellow book, they just focus exactly on this spectral analysis when you have to identify the eigenvalues and the associated eigenvectors and eigensubspaces from the scratch. And that's the first example I show you, and you will do many others in the same, following the same footsteps. Look at this. Here's my matrix. That's the matrix from my previous slide. We now no longer use any knowledge of any vectors which were given to us before. We would like to analyze this from the scratch, right? So I build my matrix A take lambda identity, which is effectively I have to subtract the lambda from every diagonal entry here, leaving the rest of the entries untouched. Here it is, negative lambda 1, 0, negative lambda 1, 0, 0, negative lambda 1, 20, negative 24, 9 take lambda. And now I will compute the characteristic polynomial of it, right? Which means I have to compute the determinant of this matrix. And when we compute the determinant, there are a few ways you can follow. There are a few methods you can follow. I'm going to use the decomposition by row or column. I think we'll go column here. It's a standard trick, right? We just choose an element like negative lambda. We cross out everything under the element, everything to the right or to the left of the element, and then that will be my minor. And I use this minor and I multiply this minor by the element negative lambda, Here it is. So if I compute that, here's my negative lambda from here, and here's the value for the minor, this minor. It's the determinant of size 2 times 2. We multiply across this diagonal, negative lambda times 9 take lambda, here it is, and subtract across this diagonal. That's why it's plus 24. Now this is not it. Then we continue. We move my cross down here because 0 doesn't give you anything because 0 just finished the term. That's why the only term which is left is this one, negative 20. So it will be 20 times this minor, which is very easy minor. It's simply 1. That's why it is plus 20. So the whole determinant is computed now via minor method. Like it or not, but with the spectral analysis, you will compute lots of determinants. So you have to develop the practice of doing this efficiently and quickly and avoiding computational mistakes, because there is something like a sign alteration there. You have to just keep track of everything when you do this. Now, if I do complete expansion, if I do a complete expansion of what I'm looking at here, it will be something like this, negative lambda cube. It will be a polynomial of degree 3, as predicted before. So cube comes if you multiply this lambda with this lambda and with this lambda. That's why it's negative, because it's 3 negatives. Square will come if you take this lambda, and this 9. That's why it's a plus 9 lambda square. Linear term, lambda, will appear if you take this lambda with this 24. And the free term is just 20. Here's your cubic polynomial. And the solutions to this cubic polynomial, the eigenvalues we need. The problem is, of course, it is not easy in general to solve a cubic polynomial. And every time you're facing a problem like this, there will be some extra hint available. Either the polynomial you'll be looking at will be easy factorizable, or some other information will be supplied to you. In this case, I will use some information from the slide before. From the slide before, we recovered that one of the eigenvalues is 5, right? So from the slide before, I can hope for that 5 will be a solution to this polynomial. Let's just do double check. Here's my double check for 5 being a solution. If I plug in 5 in here, it will be negative 125 plus 9 times 25. Take 24 times 5 plus 20. Let's just check if it is 0. It's tough, isn't it? We can argue like this. 125, it's 5 times 25, and here's a 9 times 25. So this combination will be 4 times 25, which is 100. So this one is just simply 100. 100, this one Yeah, it's this one is negative 120, and that's plus 20. It is 0. Confirmed, I'd say. But you can double check with your calculators. So you see what happens? I know one of the eigenvalues from my previous example. And now having this one of the eigenvalues, I can factorize my polynomial. Here's the factorization. Look at this. Here's my polynomial. What I will do, I will artificially create the linear factor which carries 5 as a root. Here's my artificial creation. Negative lambda cubed from here. In order to artificially create this factor, I just introduce 5 lambda square, because together these two make the factor lambda take 5. Now, because here we have 9 lambda square, here's my extra 4 lambda squares, and now I'll make another artificial factor. Take 20 lambda, because we have 24 here, I subtract extra 4, and the final 20. Now these two together, they carry a common factor lambda square, here it is. These two together, they carry a common factor 4 lambda, here it is. These two together, carry the common factor 4. You see, in every couple, I have created artificially lambda take 5 bracket. Now if I factor out this artificially created bracket, this is the expression remaining inside, negative lambda square plus 4 lambda take 4. This is a perfect square, we all recognize that. And the final factorization is like this. Spectral analysis, the beauty of it, it just requires many different techniques from many other areas we studied individually before. And if you make a little mistake in one of these areas, everything else will go ruined, to say the safe word. So it requires significant discipline to bring these different methods and technology and techniques together, and hold yourself together not to make a little computational mistakes. Double checks always help in this case, of course. So for instance here, if you went through really difficult factorization, this one wasn't that difficult actually, but if you went through really difficult factorization, I strongly encourage you to take the root you found and double check against the very first equation you had. It's the best way to make sure you haven't made any computational mistakes on the way.